Lesson number 110 is about vertical and horizontal shifts, reflections, and combinations of shifts and reflections. Now, in order to do this lesson, we need to know about parent functions and new functions. Parent functions are one we've learned about before, like f of x is equal to x squared. We know f of x is equal to x squared gives us a parabola-shaped graph, and it's going to be getting steeper and steeper as we go further and further out on the x-axis in either direction. A new function uses the parent function, so the parent function here is x squared, and then it changes it slightly. It can shift the graph up, it can shift the graph across, or it can even reflect the graph across the x-axis. Now, this new function is f of x equals x squared plus 1. Notice the new function notation is always going to have a capital F, where the parent function notation has a lowercase f. We'll use that each time as we go through this type of problem. When we have f of x equals x squared plus 1, well, the only thing that happens is you take your whole graph and you shift it up 1 unit. So you can see here I've taken our original function, it was sitting at the origin for its lowest point, and now it's sitting at 1 for its lowest point. We've got the same graph, it's just been shifted up 1 because of this. Now let's look at another one. Let's say we have a parent function of f of x is equal to, we'll say, the absolute value of x. The absolute value of x must be our v-shaped graph going out in both directions. Now if we have a new function of f of x, capital F, is equal to, let's say we have the absolute value of x, and then we'll say plus 4. If we had that, we take this and we'd shift it up 4 units. So we're going to make our graph go up higher. If we had a coordinate plane here that had values, we just put it in the right position. Since we didn't have the values, we'll fill that value in here. It's no longer sitting at the origin for its lowest point. It's sitting at 4 for its lowest point. Let's look at some more. Now a vertical shift in the graph will look like what we just saw. Our new function, okay, this is our new function, the capital F, is going to equal the parent function, f of x, lowercase f, plus some value k. When it's plus some value k, then we're going to be taking our k value and figuring out how much that moves our graph up or down on our coordinate plane. So again, here we go. F of x equals the absolute value of x. So we've got our parent function. There we go. That one came out a little bit squiggly. That looks a little better. And then we have our new function. Capital F, new function, equals the same shape, but then minus 3. So since it's minus 3, we're going to take the same shape, and we're going to move it down 3 on our y-axis. So we now have something that looks like this. We'll fill in that value, so we know that it sits at 3 on the y-axis because it's been moved down 3 units. That's what a vertical shift looks like. Let's look at some more. Here we've got a parent function, f of x equals the absolute value of x. Or sorry, pardon me, f of x equals the square root of x. We were just working with absolute value before. Since this is the square root of x, well, we've got that half parabola shape and it's opening to the side. Our new function, capital F, is equal to the square root of x minus 1. Now notice this time the minus 1 is within our square root symbol. It's within everything that we're working with. It's not outside. Let's look at what happens to that. Let's use a table. Let's say we have x and we have f of x. This is our new function, so we use that capital F. Let's say x equals 0, 1, 2. So if we have f of x equals the square root of x minus 1, and x is 0, so instead of writing x, we're going to write 0. 0 minus 1. Well, if x is 0, then f of x is going to equal the square root of 0 minus 1. That's the square root of minus 1. Well, the square root of minus 1, we're not able to solve that one. So we're going to put a question mark. Can't solve. No real answers. Let's say we have 1. Square root of 1 minus 1 equals the square root of 0, which equals 0. Perfect. So when x is 1, f of x is now 0. If x is 2, 2 minus 1 equals the square root of 1, which equals 1. So we come up to 1. What you can see has happened is this graph has moved over 1 to the right. We have the same shape because we used the parent function to help us identify what the new function will look like, but it's been moved over 1 to the right. This is a horizontal shift rather than a vertical shift because our value is within our symbol of inclusion, not outside our symbol of inclusion. Horizontal shifts look like this. The new function equals the old function but minus whatever our k value is. So our k value tells us how many to shift the graph up or down, left or right, and in this case it's left or right because it's within our symbols of inclusion. Let's look back briefly. Vertical shifts, the k value is outside of our symbol of inclusion, so that shifts it up and down. Horizontal shifts, our k value is inside our symbol of inclusion, so that shifts it right or left. Now this one, the k value is separate from the minus sign. If we look back at the last one, our k value was 1, so we shift it 1 to the right. This time, our k value is also 1. K value is 1, so we shift it 1 to the right. So we're going to take our old graph, and we're going to shift it 1 to the right. So instead of lining up at 0, this time it's lining up at 1. Let's look at what one more would look like. Let's say, I'm going to sketch out a coordinate plane. Let's say we had this one. Let's say f of x is equal to, and we're going to use the cubic function as well for our parent function, and let's say x plus 1 to the third power. Now if we had this one, and it's going to be on this coordinate plane here, in order to make this minus symbol a positive symbol, that means this value must be a negative 1. And it must be a negative 1 because x minus negative 1 is equal to x plus 1. So what that would look like in our shift is, since it's moving minus 1, it's moving backwards 1, we're going to take it 1 over to this side. And we're going to have our same function, it's just going to be moved 1 to the left rather than 1 to the right. Horizontal shifts happen when our k value is within our symbol of inclusion. Here's our final type of reflection, or final type of movement that we have today. This one's a reflection about the x-axis. We have our new function equals the opposite of our parent function. Well, if it's equal to the opposite of our parent function, we must take our parent function and make all of our output values the opposite. So what that means is it's going to reflect over this line, over our line here that we have for our x-axis. So our new function of negative x squared equals our parent function flipped over the x-axis. We're going to practice more with this, and we're going to include practice with both combinations of movements on the y or x-axis and reflections on the x-axis. We'll do that during our lesson practice in class, page 465. Make sure your notes are complete, and I'll see you soon.